Welcome to Astronomy, Chapter 4. In this video, we're going to look at the fourth chapter in our text called Atomic Physics and Spectra. Now, that name sounds pretty intimidating. This is a title that makes some people think, whoa, what are we talking about here? But really, this is a very short, brief chapter, and we're only going to look at the concept of atomic physics on a very sort of a surface level here. We're not going to go into great detail, and we're not going to talk about it in great depth. We just need to have a basic understanding here. But in the first thing out of the gate that you need to know about atomic physics, and they talk about it and you can see some examples of it on page 107. They show you here these different glowing objects creating these different light. The thing that we need to know that is crucial is that the temperature of whatever object it is we're talking about is directly related to the color of the light it emits. So if light is being emitted in the visible spectrum where the human eye can see it, then the color corresponds to its temperature. Now, many people may know that, like, say, for example, a candle. A candle will have an orange flame on top and a blue flame on bottom. And the orange flame is hot, but the blue flame is really hot, right? And that's because the temperature depends on the light, the color, right? They are directly related to one another. So that concept ends up being useful not only when we're talking about candles, but also when we're talking about stars, right? And the star that is most in question that we want to look at is, of course, our own star, right? The sun. And so if we take the light coming from the sun, we see that the sun generally looks yellowish, right? Well, it looks yellow because of its temperature. But we can actually do more than that. Because what we can do is we can take the light coming from the sun and we can put it into a device we call a spectrograph and help us understand what it is that is in the sun. Now, this is a fascinating part of astronomy. And I'm going to use an analogy here to help make this make sense. My analogy here is a tube of chapstick. Okay, I have some chapstick sitting here on my desk. And on this, on a piece of chapstick, we have a barcode. And of course, everybody probably knows what a barcode does, right? This is a unique pattern of lines and numbers that when we pass it through a machine, it knows that this is a tube of chapstick and it's not a sack of dog food, right? Because of that unique pattern of lines. Turns out we can do the exact same thing with light that is being emitted, especially from stars. And so what happens is we see light that comes out, and it comes out in these unique patterns, right? And these unique patterns are what we call their spectra, or their spectrum, right? And the key part to all of this is what you see on 4.3. This one statement alone explains the important idea, and that is each chemical element produces its own unique set of spectral lines. In the same way that a tube of chapstick has its own barcode that's different from the barcode of a sack of dog food, each chemical element, all 100 and some odd of them that we have a unique spectrum. Now, only a handful of them actually show up in stars, but we know this to be true because we can see this in a lab setting. So we can take, hydrogen and energize hydrogen and see the light that's coming off of it and tell what its spectrum is. So we create a catalog that explains these, and then we can compare when we look at the stars, which is very exciting. It means we can essentially tell what is it that a star is made of. Which is a fascinating part of understanding how this works. Now, why does all of this work? Why is that? Why does an element, why does, say, for example, hydrogen have a unique spectrum to helium? Why do they look different? Well, the answer is in their makeup of the subatomic particles. Hydrogen and helium have different numbers of protons, neutrons, and electrons. And when they are energized, they will emit light differently. And we're not going to go into great detail about why that is or the energy transfer, the laws of conservation of energy. That doesn't matter right now. What you need to know is that specifically the electrons do a vast majority of causing this light to be emitted at a unique pattern, the spectrum. So, because then every element has a unique number of protons, neutrons, and electrons, that means every element is going to have its own unique spectrum. Now, the next thing we need to know with that then is if we know the spectra that they're going to be emitting, on page 121, they talk about a very important phenomenon we know as the Doppler shift. Now, the Doppler shift is crucial in modern astronomy because what this does, the Doppler shift, is what explains relative motion of two objects. Now, you've noticed the Doppler effect before, no doubt, in your life. If you've ever noticed a police car or a fire truck or any siren object passing you in a car, we hear that change in the pitch of the sound. Where it goes, right? And it does so because the wave is being compressed first, and then it's being stretched after it moves away from you. Interestingly, light does the same thing in terms of being compressed or being stretched out. So if it is moving towards us, that wave is being compressed, and we say that the wave is being shifted towards the blue. The spectrum gets blue shifted. Right? And if the wave is moving away from us, the object is moving away, the wave is said to be red shifted. With us, so we see the wave being stretched out. So this Doppler effect ends up being a crucial part of understanding modern astronomy in terms of measuring, say, the relative motion of galaxies. Are they moving away from us or are they moving towards us? And that information has been immensely useful in understanding the overall nature of our universe. Now, that will cover most of the important parts you need to know about what is in chapter number 4. So, make sure you're keeping up with the reading. Take a look at the PowerPoint associated with this chapter. You should be ready to start the chapter 4 homework. Good luck.